let's grab seats and get going. Okay, so I have one quick announcement. We're going to have one more talk after MT's talk. MT's going to try and finish in a reasonable amount of time, and then Sid from Oxford is going to give us a half-hour talk afterwards, so there's some bonus material today. Okay, MT. What more can I say about MT? MT's like a UBC legend. He's the person behind the Undistinguished Lecture Series, which I think is still running. Okay, so you graduate from here. You were office mate with me and David Duvno, who you may have also heard of. You're now like not full professor, but equivalent to full professor at RIKEN. So untenured full professor. RIKEN.
It's a thing.
He's had lots of interns like Vaden and Wu and so on up here. He's probably looking for interns now. Very cool building in Tokyo, and lots of cool work on a whole bunch of different projects. Probably most well known for variational inference, I would say, right? Yeah. Okay, let's welcome MT.
Okay, well, thanks for the lovely introduction. This room has a lot of memories for me. And I've come here every Friday for like 5 years. And, you know, all things happen. And lots of good memories. So very good to see you all. And so yeah, you called me MT. It's a lot of other letters, but you can ignore them. And what I will talk about now is a short version of the tutorial that I gave at NeurIPS just a few days ago. And if you haven't checked it out, you can actually watch the full thing. It's online on Slides Live and also on YouTube. And this thing that I'll talk about is a little bit of shorter version of all of that. So I usually motivate what I've been doing by telling people the goal of my research, and it's it's very easy to understand if you know what machine learning is about, right? So I want to understand the fundamental principles of learning from observations, learning from data, and I want to use these principles to develop algorithms that learn like us, like human beings, like animals, and in general like living beings. So when I say this to people, then they always ask the questions like, what does it mean to learn like living beings, and why is this important, and why should I care about this? So I give this example. This is my daughter when she was 6 months ago, and if you see, this is a human learning, trying to figure out what she likes and what she doesn't. And she doesn't really like the sheet, and she likes the fretboard and the sound that comes from it. And as she lives her life, she figures out what she likes in the world and what she doesn't like in the world. I mean, machine learning sense, you could say she likes to generate data that she likes. These are the experiences that she likes to see more and more of, and she goes on to live her life and continues to do that. So this is after 6 months, she's figured this out, right? And she's figured this out, that the sound that comes off from the ukulele, she likes it, and she's figured it out by doing interaction in small chunks. So she doesn't have like all the information in the world. She's sitting in a small room in the house, and just with us, and just touching here and there, doing small interaction, seeing the world in a very small way, and still be able to learn about what she likes and what she doesn't, right? Which is fascinating. And it doesn't stop here, and if the world around her adapts, changes, she adapts to it, and she finds, so this is a bigger instrument than ukulele, but she can now produce the same sound, which is the same experience that she likes in the world, that she has figured out before. Now she's able to generate it, right? So my question is that this is just incredible. So this is how people learn, how animals learn, how living beings learn, is that they perform lifelong learning. They learn from small chunks of interaction in the world, and they do that even when the world changes. And they adapt to it, and they continue to learn in this world, right? We all do that. But if you look into the machine learning side, the things that we are working on, and the whole community is focused on, is something like a bulk learning, where we think that the world is very stationary, that all the information that we need to live our life lives right here in front of us. And then we compute these gradients, and we suck them into the neural network, and we take steps. So it's very it doesn't make any sense, and my research has been sort of bringing the two worlds together, because the left-hand side is something that makes more sense than doing the right-hand side, but the right-hand side really works right now. So the question is, how do we kind of put these two things together? And that's what I've been working on. So when I have been looking into things of how things should be, well, the closest framework that I can find to human learning is, the math that you write is the Bayes rule, and it's the Bayesian learning, and it's not just me. There have been lots of research that people have done in neuroscience, in psychology, in economics, of how sequential updating should happen when you see new information. And the Bayes rules just sort of gives you many in field people talk about optimality, and it does the right thing. But the issue is that when you start doing that, it conflicts with what is happening in machine learning. So, deep learning people would not like to use Bayesian stuff because it's just insane. It's computationally just a nightmare. So what I've been doing in past few years is that I'm trying to show is that the Bayesian principles are these general principles that subsumes many other type of things that are happening in machine learning. But I don't just want to talk about, I don't just want to be the usual Bayesian who just comes to you and says, you're Bayesian, you're Bayesian, you're Bayesian, And that's not nice, right? Because you're working very hard in your field. And I don't want to just say that, I'm better than all of you because you're all doing what I'm doing, right? But rather I want to give you a general principle, a practical principle that gives you a way to think about what already exists. And not only to explain those things, but to design, improve, and generalize what already exists. So my focus has been in algorithms because this is how we implement things. And I don't just want to talk about principles as general principle, but I want to show you that the code that you run, every day as a machine learning person also runs on the same principle, and you can derive it. Not only that you can derive it, you can generalize and improve it. Okay. So next few minutes I want to spend on just going through some of these ideas. So the main idea is to compute approximations to start with the Bayesian problem, do approximation to the posterior, then we derive lots of existing things. And then once we are able to derive many deep learning algorithms, Bayesian algorithm, approximate inference algorithms, then we'll try to look into how they help us to design new algorithms. And new algorithms that would do something more like what humans would do, or living beings would do. So like understanding uncertainty, understanding how important your training data is, and then going towards lifelong learning. So that's the summary for the talk. But one thing that you might want to remember is that I'm not trying to sell that Bayesian stuff is good stuff and that's the way to go, but I'm trying to say that we are all doing very similar things. And we all have very similar goals, and the Bayesian principles actually help us connect the worlds and then borrow strength from these different worlds. So I'm trying to unite people together, empower them to solve problems that we aren't able to solve right now. Okay? So that's my hope. Feel free to stop me anytime, but I just have to finish this in just 40 minutes, which is like a really long time. So please stop me. And then I can tell Mark that questions are taking longer, and I can take 1 hour maybe. Okay, so I'll start with contrasting with what is deep learning and how different it is from Bayesian learning, and why I think that the Bayesian learning can really help to take us to lifelong learning. So deep learning, most of you probably know, it's like empirical risk minimization or maximum likelihood principle. It basically has this principle of trial and error, where you have some data points, and then you have some model with some parameters, and you say, I'm going to predict the data, write some loss over it, and I'm going to minimize the loss. Right? And this example could be regression. So like this is a deep network, this is input, this is output, take squared, add a regularizer, minimize. And then you can minimize using stochastic gradient descent, or like some variant like RMSprop or Adam or Newton method, and they all look like this, right? And this works great. So it scales well to large data and complex model, and very good performance practice. But then we believe that this will just kind of solve all problems, right? And it's not at all true, unfortunately. So it's a counterexample to make you think a little bit more about what could be wrong with this approach. So look at this classification problem. There are two classifiers, two classes, and I give you two classifiers, red and blue line, and I ask you the question, which line is a better line? Blue. Okay. How many of you think blue line is a better line? Okay, and how many of you think red line is better line?
I saw your tutorial.
He knows the trick, right? It's a trick question because I want to break your usual notion, right? So the point is that if you think that this is your world and this is what you cut out for, this is what you want to do. You know, when we are young, we usually think like that. We think that whatever we have right now in front of us, we are very, greedy, and we choose the solutions that will, right? But if the mistakes that you make right now are going to come and hurt you in the future, okay? so suppose your data set, the next set of data points that you got were like this, then the blue line would not be the right line. Right? So you're not wrong if you say it's blue line because you said that based on your current, best possible guess. So it's right that this is the best line because it has the minimum norm and it's kind of perpendicular, maximum margin, lots of intuition on why this should be. But this solution is also not bad. Right? So you're uncertain about which solution you should choose and you're saying, oh, this one looks a little bit less probable than other. But actually both solutions kind of okay right now. But if you make a mistake right now to pick one, because you have to pick one because you're a deep learning person, right? And then you encounter this and you're done, right? You're like, now I have to retrain everything. I have to store all the data points, right? And that's the issue here, is that when you do not know, and you do not know how much you do not know, and then you have to make these choices might be wrong choices, and then you're going to pay for it in the future, right? And so the Bayesian solution for it is like, let's not lose these things in the beginning when we are not sure. When you're not sure, I don't want to give up on good options. Okay, and it's called uncertainty or posterior distribution and all that. In math, it's written like this. So you say, I'm going to sample a bunch of things here, so a bunch of lines, and I'm going to rank them how good they are. Right? So if I do... So D1 is the first datum, and if I do that, I get a sort of my belief over what is a good solution, what is a bad solution. And in this case, as you guys were saying, that the blue line is a good line, well, this line seems like the most probable, but this line is still there, It's there in your solution space. So you haven't because you don't know, you need to be wide enough. You need to say that, I don't know yet, what would happen in the future. So I don't just want to start doing computer science and regret it later on, Things like that. So you want to keep this variance around, and that's what this rule does. So this integration actually normalizes things and gives you all of this, variance around things. And then when you get your next set of data, you go like, oh, all of my options were wrong, but I still have this guy lying around with me. So I can actually update my belief. And then what you can do is that instead of sampling from the prior, now you put your posterior as the prior, and let's not go into the math, but the point is that you can basically ignore the first set of data points and you can just focus on this, and you say, if I sample these lines, well, these will come more often, but then they will misclassify this data, so I'm going to run this Bayes rule again, and I will find that this one is most likely. Okay? So if you work with distributions, then you are actually doing strictly better, more than what the optimization rule will give you. It will give you just one solution. If you keep your options open, the distribution tells you that don't be too greedy right now. And then as you get more data, maybe the world becomes more stationary, you see more of the world, then you form your opinion of what you really like and what you don't like. But don't do this in the beginning. Yes?
What if our models are misspecified?
Yes, so it doesn't matter. It's the same. So the rule looks slightly different if the model is misspecified. So you have to temper this thing. So that's one way to do it. So you have to temper this with something. The main idea goes beyond this. The main idea is that if you know that the things are going to change in the future, I don't want to trust everything right now. And I'm slowly going to form my belief. The rate at which you're going to form your belief could come from posterior distribution, the variance that it gives. But that might be also wrong if your model is wrong. But then you can also kind of discount it a little bit. So there's something called tempered posterior, and with that you can fix these things.
Just can I say one thing?
Yes.
I'm just curious. So there could be a situation in which paying extra for this benefit doesn't give us much payoff in expectation than just to go with the most likely model that we can derive if there's a model misspecification going on, if you don't understand the approximation error and many of those things. Any comments on that and how it relates to this?
Yeah, so the theory actually says that the same kind of updating will get you to the right thing, but the main idea of the theory is that don't trust things too much, and the base rule, the model will give you some kind of what it doesn't know, but the model is also not right. So you need to put exploration, exploitation on top of it. Maybe in the end I talk about this. There's two principles, estimation and exploration, exploitation. Right now we're talking about estimation. Okay? So exploration, exploitation can fix many things. Okay. So because I don't have time, but the word that I want you to remember in all of this, and really if you don't are not interested in anything after this, it's okay, you can ignore it. This is the most important thing that is important, that is useful for now, is that the global property is that you're not thinking about just fitting your data well right now. You're thinking about, you might not really know. Maybe your data is not enough. Maybe something else is going to happen later on. So you're actually trying to maintain your belief it's like a global belief. You're looking into more option than one option. Okay? And this is the main difference between Bayesian learning and deep learning is what I would say. Everything else, there's lots of details, but the main point is that in deep learning you do local updates. You look into your data points, you compute gradients, and gradients are very local information of what's happening, in your model when you're minimizing things. But when you do Bayesian type of stuff, you look into many options, and it's actually global in that sense that you're looking at many lines. If you don't understand what that means, just think of like having many lines instead of having one line. Okay? And the global property sort of helps you to estimate uncertainty, to do the sequential thing, but it makes scaling, training and handling large data, large models difficult. And that's where the trade-off comes in. And that's the key point that I would say. And what I'm trying to say that if you're doing lifelong learning, there is no way you shouldn't be just paying attention to your data right now. Okay? And you should be sequentially modifying your model. And you want to keep your options open in the beginning. And Bayes kind of update is actually your only bet. So this is just indispensable for doing lifelong learning. Okay. So that's the claim I would make, and we can discuss about this maybe later on. You can disagree with me, but I would want you to think about this. Okay, now that I have kind of maybe made my case for why deep learning is not enough and we should be doing more, let's go into why deep learning algorithms can be explained by the same kind of update. So this sequential prior-posterior thing that I showed you, it looks like it's very, very different from taking derivatives and using SGD. So how are they connected? They look very different, so, what's the point of this? So what I'm trying to show is that, actually deep learning algorithms like this can be derived from the same principle if you write the principle in a way that it kind of looks similar. Okay, so it's just kind of changing point of view and introducing the main idea of posterior approximation. So you start with a Bayes rule, then you make approximation to the posterior, and when you make more and more approximation, like you go from more global thing, like keeping all options around, to more local thing, like keeping one option around, you start getting things, that look more like deep learning. You'd expect that, right? That if you start with the global solution, but then you do a huge approximation to do local thing, then you should get back to what you're doing in deep learning. And that's basically what I'm going to show. Okay. And what will happen in the end that, we'll get this kind of algorithm. So what you should remember is that, so if you run optimization, it gives you this one line. But if you run these kind of methods, so this method called VOGN, which will be very similar to this, but then you add a little bit of global touch. You say, I'm going to keep many options around. So I don't know if you can see, but then this is the mean of the Gaussian, and these are the other options, red lines that I'm sampling around. Actually, the projector kind of, this is, sorry, I should stay here. These are red lines, the other options that the data can be classified with. Anyway, this will become clear soon. So Okay, I've taken 20 minutes already, and I have 20 more minutes to go. You can watch the details in the tutorial. Okay, so let me just give you the crux of everything. So the main idea is start with the Bayesian problem. So write the Bayes rule, but don't compute the posterior exactly, but approximate it. And to find the approximation, use a learning rule, and the learning rule is going to look a lot like optimization problem. Okay, but it's actually solving a Bayesian problem to estimate it, to estimate the approximation. Then if you go from very simple approximation to complex one, this side will be more like deep learning, and this side will be more like Bayesian. Okay? Tell you a little bit more specific thing. Think of the posterior distribution. The ultimate thing that you want to get looks very complicated, like this. And I'm going to do a very crude approximation like a Gaussian. It's a circle. I'm going to put it somewhere, but I can only change the mean and not the variance. Okay? And you know, like you're going to put it somewhere near the mode. And if you take this Bayesian learning rule, try to find the mean of this Gaussian, then it gives you gradient descent. Okay. Then, if I increase the complexity to estimate both the mean and the covariance, so now I can tilt, change the shape of the circle. It's a covariance. And then I'm trying to find both the mean and the covariance. And if I plug into that Bayesian learning rule to estimate the mean and the covariance, to get this posterior approximation, this will give me, you can guess it actually, it will give me Newton's method. That makes sense, right? This looks more degree of freedom. Second order information is added somehow. And then if I do a mixture of Gaussian, can anybody guess? Now you have multiple Gaussians, right? So you can do ensemble of Newton. So now you're running multiple chains to estimate each of these Gaussian, but then you're trying to push them to get more global effect, to push them away from each other. Yes?
This looks like particle filtering.
Yeah, so actually that's what it should have been like, but the problem is that the theory of like how you put the particles around, it's motivated by this random walk stuff where you're trying to explore, so it's very hard to mix, and you don't really specify the approximation before.
No, but the intermediate, it looks like I think the unscented Kalman filter.
Yes, they're special cases.
The intermediate, yes. And they finally.
Yeah, that's the main. Yeah. So they are special cases. Yes.
Oh, okay.
Exactly. Here, the focus is that you write one rule that gives you everything. So, of course, you should be able to draw. So EKF is actually a special case. It corresponds to Laplace approximation, if you know. Then, if I continue to increase this, I should get like higher order methods that capture more about the landscape, more global property about the landscape. And if I continue and I plug in the Bayes, the exact posterior, I get the Bayes rule. And that's going to be hard. But the point is that you can unify everything by using approximation. And then you have to make these things like going from global to local thing. And that's the main idea. If you do that, then things make sense as they should. Okay? So math is actually less important, and we don't have time. So I just walk you through rocket speed. So first we start with approximation, so we want to specify, and we stick with natural parameterization of exponential family. So approximation to the posterior, like Gaussian, mixture of Gaussian, not mixture of Gaussian, not really exponential family, but you could do that there too. But let's just think in terms of exponential family. This is natural parameter. The other thing that, for Gaussian, you can write this quadratic in terms of like theta, and the linear term and quadratic term, and the things in front of it are the natural parameter, okay? So don't see the detail, don't worry about it. The other thing that we need to know is there's another parameterization called expectation parameterization, which is expectation of the sufficient statistics. So for Gaussian is expectation of theta, which is the mean, and expectation of theta transpose, which is the correlation matrix. Okay? Don't worry about the detail. Just remember, these things are not important for the talk. Remember that lambda is one type of parameterization, okay? Which is natural parameter, and mu is expectation parameterization, which is another type of parameterization. And that's all you need to know. Okay? And exponential families always have these two parameterization, and they're actually kind of connected to each other. There's one-to-one in many cases, one-to-one mapping between the two. So what we're going to do now is that we're going to write this Bayesian learning rule. So think of the optimization framework that minimizes this kind of loss, but then we're going to do something like minimize something like this. So we're going to still look at the loss, but we're going to now do something more global. So we're going to introduce this distribution and think of this as sampling these lines. This distribution gives me a way to sample these lines. The question is like how wide or narrow or where should I locate the mean? So the parameter of this Gaussians are known. Ideally it should be the posterior distribution, but I don't have that. That's the problem that I'm trying to solve. So I'm trying to find this Q, and this will be like exponential family. So I'm trying to find the lambda, which is the natural parameter. Okay? And I'm going to add a penalization to keep the distribution interesting. Like entropy, like I want the solutions to differ from each other, like in particle filtering. So I want the entropy to be penalized. That's the main idea. And if I want to recover these algorithms from that, then I have to do certain global to local approximations so that I don't look at many solutions. Okay?
The fact that you're choosing one theta means you're doing a local. Is that how
Yes.
I interpret that?
Yeah, so this is gradient in the AI.
You don't have the distribution in this form.
Sorry?
You don't have the distribution.
Yes.
You're just choosing one.
Yes, exactly.
Okay.
So that's deep learning. And this is more like Bayesian learning. Actually, this is equivalent to Bayes rule. It's just, I don't want to introduce probabilities because people then don't pay attention. So this is actually another way to write Bayes rule, and the references are there in my talk. But this goes to exact posterior if you let your family of distribution to be the everything. But we can approximate this to be just exponential family. And now our goal is to find lambda by minimizing this. So this versus this. And what I'm saying that if you minimize this with a particular flavor of algorithm, which will look very similar to what we do in deep learning. So deep learning does this to, or optimization methods do this to minimize this. Or we're going to use a different algorithm. So that algorithm looks like this. Okay, so they both look kind of similar, but the top one is only trying to find one theta. And the bottom one is trying to minimize this, but it's trying to update the distribution, the parameter of the distribution. Okay? So like natural parameters. In this case, mean and variance, something related to that. And the key point is that I want to take the gradient with respect to the expectation parameter. Okay, so usually if you run the gradient descent on this objective, this should be lambda. Okay, this is where everything differs. Small change. And many years people, said to me that, oh, you're just doing one different variant. Why should it be so important? But what I'm trying to say is that if you did this, this can be obtained as a special case of this. Many flavors of that algorithm. And many more. Okay, there will be a big chart that I'll show in the end. You'll see that it's related to almost everything. Well, many things.
I know you said you don't want to talk about probabilities, but where in that formulation is there's a prior factor in?
Yeah, so typically, no, I want to talk about probabilities only when you ask me. Loss is log of joint for a probabilistic model. And then you can see when you take the derivative, you'll get Q to be proportional to joint, which is the posterior, if this was not restricted. Okay? This is strongly convex in KL divergence. That property has not been exploited yet. But it's insane. Even if this is non-convex, this is convex. And so there's only one posterior distribution. This has not been used. This is remarkable why sequential updating actually works. Anyway, so what we'll do very quickly now in Flash is to say that we're going to choose different approximation. Okay, so we're going to choose different approximation. So we're going to start with a very simple one, expand it, and then we'll get different algorithms. Right? Make sense? Any question? Actually, this is an important slide. So, any other questions? Okay, good. So I won't go into details, but usually in my talk I just kind of start with a gradient descent look like this. So my claim is that if you choose a Gaussian with fixed covariance, so for scalar cases, the mean and the variance could be anything. Actually, I've chosen it to be 1. And then you take the Bayesian learning rule, and then you define lambda and mu. You plug that in. Okay, you plug that in. It looks kind of straightforward. The entropy is entropy of a Gaussian is constant, so it goes away. So no exploration is happening, but there's this thing. Then you have to make an approximation. So here is the kind of key thing. So you see that this rule actually looks like this rule. So this m is the mean. But the difference is that you're computing the gradient of an expectation. Meaning that you first sample from your Gaussian many lines, and then you compute loss at those, and then you take the aggregate gradient. Okay? So this is a global operation. If I wanted a local operation and only at one value, what would I do? Is the question. Okay? And you would do what anybody would think of is that just approximate at the mean. Right? Don't worry about the variance. Just look at one solution, which is the most likely of the Gaussian. So that's what this line does. And this is called zeroth order delta approximation in statistics. And there's, it might seem very greedy right now, the way I've written it, but it's a very fundamental thing. So you're basically saying that I'm not going to look at the average, I'm only going to look at the loss at the average. I'm not going to look at the average of the loss, I'm going to look at the loss of the average. So it's the loss of the mean. Okay. And if you do that, then you can just plug in and you see that this kind of comes here, right? And then call mean to be theta and it's equal. So these two things we'll do, right? We choose the approximation, we go from global to local. Because we don't want to do a Bayesian inference, we don't want to do exploration, so we lose that property. If you lose that property, then we do what people do in deep learning. This is the idea. Same thing happens. So you could plug in different gradient, you'll get stochastic gradient, then let's not get into that. Then you go to Newton method, you start with the same thing, you say multivariate Gaussian, mean, and the precision is the inverse of the covariance. You write lambda, you write mu, you go in there, you look into the entropy term. Well, there's a property that the gradient of the entropy with respect to mu. This is related to Bregman divergence, if some of you are from optimization community. So this always happens with exponential family, yes?
So which theta is being used in that formula there?
In the previous one? In the SGD?
The one that just appeared, the lambda update. Which theta is that?
The sample from Q. So lambda is sitting in here.
Okay, I see. So Q is parameterized by lambda and its domain is the thetas.
Yes, and you sample from theta, so theta is averaged. Then this whole thing is a function of lambda.
Okay.
So you take the gradient with respect to mu, because you're crazy. So that's the point. All of this work actually done by Wu, who is sitting right there, who works with Mark now. So, the first paper that we wrote with was me and Wu, when Wu was unemployed, I think. Probably very important work that he did. So yeah, you do this kind of, you plug this thing in, you do some rejuggling, entropy's gone, and now it looks like this, and you saw like, oh, this looks very different from this, but then you will start putting this definition of lambda and mu inside. So you put the first one, you put the second one, you do some tricks. So there's a lot of math going on. I know we can't go through it. So in tutorial it actually worked, but here. So what I'm trying to say is that this doesn't look like Newton method, right? It doesn't. It's just nothing, no similarity. But I don't give up. I keep working on it. So the main thing that's missing is that here there's gradient and the Hessian, right? But here the gradient is with respect to these expectation parameters, this mu that I defined. So the key point is, how do I go from here to there? Okay? And then actually this is one of the most fundamental thing that makes all of this possible, is that these gradient with respect to mu are actually related to the gradient and the Hessian. Okay, of the original thing. So this identity has been actually used quite a lot. 2009 is probably the first time that I saw it, but this goes back to like Bonnet and Price's theorem, it's called, and it's very, very old. But it's basically saying that if you have a Gaussian and you're taking gradient with respect to the expectation parameters, they're actually related to the gradient and the Hessian. So first order and the second order information. In the previous case, you were taking gradient with respect to the mean, and that was related to only the gradient. That's the first order information. When you add the covariance to your approximation, then you're adding both the gradient and the Hessian. And this is the key point, and that's why I want to take the gradient with respect to mu and not lambda. So my own community said that this to me for many, many years, that why are you doing this? This sounds insane. But I'm trying to make a point that this is very, very fundamental. If you want to ask questions about a landscape, about higher order information, then you need to take the gradient with respect to this different parameterization. That gives you this thing. Okay, so then you do global to local, you plug that in, you do a little bit of more math, and then you see something like this, and then you say, I'm going to choose the step size to be 1, and then I get the thing. So I'm going to go into detail, and Mark will probably ask why step size of 1, but okay. So from there we actually went to, we said let's not choose the step size to be 1, and let's look into this rule that I just derived in the previous one and compare it to RMSprop. And it turns out that RMSprop has very similar thing. So when you don't believe that your updates are kind of, when your system is noisy, you don't get, so I'm not finishing in 40 minutes, I'm sorry. 35 minutes right now. And I'm halfway through, but I'm going to, But this is an interesting point that when you look at this update, this actually resembles many things that you see seems to be working in deep learning. So this update rule is used in RMSprop quite a lot. This has been used in many type of RMSprop-like algorithm where you're trying to do some kind of moving average to damp the noise in your stochastic gradient, and that appears in the Bayesian principle, the one that's derived from Bayesian principle. So the point is that then you do a lot of approximation here to go from global to local, and you choose your Gaussian because this is like scale vector, not a scale matrix. So you let the Gaussian be diagonal. You do all of this. Okay, and then you go from here to there. That's the point. And then if you add some heavy ball term to the Bayesian problem, you get Adam. And this, I can't insist that this is amazing, and this is what Wu did actually. So he had written a 3-page proof on how this actually works, and it's magical when you invoke the right principle and you work in this distribution space. The algorithms that you have actually designed in the parameter space, they just pop out of this, more universal thing. So this is all there in this paper actually, if you want to check it out. Anyway, to summarize. Gradient descent is derived from Gaussian with fixed covariance and estimating the mean. Newton's method is using the multivariate Gaussian. RMSprop is using the diagonal covariance. Adam is obtained by heavy ball momentum term. Everything with that same Bayesian learning rule. Right? This is not done these are not really hacks. These are principles that if you change the approximation complexity, you get more complex algorithm. But if you want to not do the new, optimization, so if you don't want to do the Bayesian thing, then you make this kind of go from global to local, and then things work. So now that we know that things are at the same place, we have a method from which we can get the local methods, like local algorithm, like optimization methods. Then, if you want to do something like Bayesian, then we just gotta go slightly global. My goal is not to make things perfect. My goal is to improve things. So I'm just going to start doing not really greedy things and start looking into more options around my mean. And that's the kind of point that we did. So this I don't have time. Before going there, I will just say that there is a huge set of algorithms that come out of this. But in my tutorial, I talk about least squares and forward, backward, and all of the Bayes rule, the exact graphical model, what people use, all of this. Then Laplace approximation, stochastic variational inference, message passing, even EM, and deep learning, they all can be written with this. It's all this whole thing about, finding the right approximation, doing the factorization, or going from global to local. And I've been trying to write all this down in this paper, but it's really in the preliminary phase even now. But you can check out, it's has 5 pages right now. It summarizes all of these things and points you to the right references. Okay. If I've convinced you with that, then I just go into, I'm just not going to go there. Okay. So this thing that I was talking about, right? So now I'm going to try to talk about how this helps us to improve deep learning. And I'll take maybe next 10 minutes to do so. So I think we'll be okay with time. not 40 minutes, but yeah. So think of this problem, right? So you had these clusters, and if you did optimization, it'll just give you one line. But if you start doing this, like adding a little bit of global touch, then now, the blue line is what the optimization algorithm like Adam would do. But this Bayesian-like algorithm, which we call VOGN in this case, gives you the mean and gives you this variance around. So this thin line that you see, they're sampled from the Gaussian. And the code is almost identical for the two. So it's very, very similar. But now you're getting this sort of uncertainty. So you don't know, you realize that you don't know what to do here because you don't have much data. It's actually telling you something away from the data. It's giving you multiple options to not be overconfident right now. But I hope that makes sense too. And the key idea is actually just kind of start with RMSprop and just add some exploration. So like instead of looking at just the mean, now look at samples from the distribution. So that's one line of change. And turns out that if you wanted the right variance, because you won't do something like Newton method, so this has to be second order information, so don't do what they do, but do something slightly different. And if you did this, then the variance can be just read from the scale. So this it's just there, because it's the covariance that you get with your RMSprop. So my point, if you don't get the detail, is that just change slightly things, just add the global touch, and then you get the variance. How good that variance is still questionable, but it's very easy to run. So this is all, you can download this code and run this thing. And we've used many practical tricks of deep learning. You just kind of switch from Adam to VOGN. It's one line.
To go back to the equations, it's basically like RMSprop, except that you're kind of like sampling the gradient over multiple.
Yes.
Okay. All right.
Great. Okay. Essentially that. So because the form of the algorithms are so similar, it's easy to take strength from one side and put it into other.
You just take one sample or multiple?
In our experiments, we were doing one on ImageNet because it doesn't scale, otherwise that's fine. Yeah. So it's just slight. Again, we want to improve things, not make them perfect. Yeah. So if you do this, you get this kind of result. This is like segmentation on video, and this is the uncertainty. Right. This is not the best result that one could get, but this is where we are right now. But you can improve this. This is like entropy is telling you that you don't know at the edge. You're not very confident because you can't segment them properly. You can take this and you can run this on ImageNet. So this is like one of the first results that has been able to scale what we call variational inference in the Bayesian method world to ImageNet scale. And what we are surprised to see is that the convergence rate of VOGN is like almost identical to Adam, right? Because the algorithms are very similar, and I can make it to happen now. I can throw in the same tricks, right? But I can also get the same performance, and then I can get uncertainty around it. So I recommend you to read the paper. There's many experiments where we show that the uncertainties are not like like total shit,
Is the error on the top right, you improved on it, and that's because you're predicting the mean, not some other...
Yeah, I would like to think that way, but
or
I don't want
to... noise?
Yeah, I don't know. So SGD does a little bit better than Adam on ImageNet. So SGD is this one, and SGD gets to the same performance as what we get. Yeah, so I think it does maybe something right. I don't want to make a claim because I don't have the... but we'll see how this works. So this actually, so far, why I'm kind of really, convinced that this is going in the right direction is because we don't have to wait too long now to make things work. So let me show you more. So another thing, very, very simple stuff. So, when people learn things about the world, they know what they liked and what they didn't like, and what was important for them and what was not, right? And if you have to do kind of things that you were talking about just now about anticipation, you have to know what you knew before so that you would be able to better tell what will happen in the past, right? So here's a question that's typically not very easy to answer with deep learning, is that if I ask you, given this classifier, which data points are more important for the classifier, how many of you would say red is more important? Okay, and how many of you would say blue is more important? Right, because you understand. You can see this in 2D and you can tell, right? But when you just look at the model, you can't tell it. A model doesn't really tell you this, right? So this I call model view. But if you put the Bayesian hat on, because the Bayesian method does this global thing, because it looks at alternative options by perturbing or looking, moving this line slightly, I could tell which data points will be affected the most, right? And this really goes into what people do in the dual view, and that's the data view. So actually, if you did the data view, it should tell you that the boundary elements are more important. And if you come from SVM community, you know how to do this. But how do we do this in general, right? What I'm saying that when you define these distributions, you actually know how to move these things, how to break these lines. And they touch certain data points more. And then that gives you which points is more important, okay? So there are very subtle points here which comes to integration versus differentiation in deep learning and integration in Bayesian learning. I don't have time to go into that. I'm very happy to talk about it afterwards. But we actually sort of try to show that neural networks can be written as Gaussian processes where the data space view makes more sense. And you can go into this was at NeurIPS, and I would really recommend. This is my favorite paper, and I think this is going to change things. And reviewers didn't see it, and people don't seem to see it. But maybe some of you guys are optimization people, so maybe I can convince you that this is like global to local kind of thing, and this is a different, okay, I shouldn't have used that word. But what is actually happening that given a loss, when you do approximation, like a Gaussian approximation, you get a quadratic approximation of the loss. You can probably agree with me on that. Because it's like using the first order and second order derivative. It's like Taylor series expansion. When you actually do that and you look into the parameters that you get when you use the posterior distribution, this approximation, Gaussian approximation, you get some linear, so you convert this neural network to a linear model, and then you get some new observations and some variances on how to weigh them. Now, if you're an optimization person, you can understand what I'm saying. The variances are the dual. They tell you how important a constraint is. And the constraint in this case is the data point. So when you define distribution around lines, it gives you a way to move these lines. Oh, I can move this much. Then you know which points you're going to hit first. And that variance tells you the importance of the data point. This is the thought. So this is actually related to convex dual, and hopefully the next paper that I write would show all of these connections to, convex duality. People do this in pricing, where dynamic constraints come in, which constraints are important. This is related to this huge field of thinking about problems with duals, with constraints, of which constraints are important, which constraints are not. And they're important for you to tell what's going to happen in the future, okay? So here's a simple example to convince you why this is important, right? So if I did this in MNIST, right? You could do this right now. If you read the paper, it takes this pre-trained model. Look at the least important ones. They look like the ones that are very far from the boundary. And look at the more important ones. They look like they're outliers, right? They're boundary. They're the one that's most likely to switch parties, They lie at the boundary. Same thing for C410. Least importance are very, very regular shaped, but the most important, which lie at the, for you, you're not very confident about them. So you see the point about thinking about, I'm uncertain about things, I'm looking into more options of explaining my data, tells me which data points are most vulnerable to things, right? So it helps me interpret data points. You can write kernel matrix, you can look into similarities, all of this is in this paper. Say you should read it, and this is related to, people talk about MTK and all this, neural tangent kernel right now. Neural tangent kernel just pops out of this. I don't have to do any functional kernel gradient descent or infinite dimensional, neural network. This is sort of finite networks. I get MTK out of it. Okay, so this connects to a lot of things. Okay, how does it? So last part that I want to say, now I'm going to finish in the next 5 minutes, is that people have been trying to do lifelong learning, so one type of thing that they do continual learning. so this is like on CFAR 10, CFAR 100, you start with 30 classes, and then you train your network, then you get 10 more classes, and then you try to train again, and you can't see the past classes now. Okay, then you get 10 more classes, and you can't see the past thing. So this one's showing you these tasks, so 10 classes each. And your hope is that you want to reach in the end, you want to reach as like, if you had all of the data at once, so call this joint training, you want to reach this performance. This is the performance that you get if you had all the data in the world. Okay, so this kind of deep learning side. But we want to do more like human learning, so we want to do this sequentially over time and not perform badly on the past things because we can't see them again. So what people do right now is that they do this kind of, so forget about these things, but just look at EWC, is the DeepMind paper that came in 2016, which does Laplace approximation, which is a crude Gaussian approximation. And this one actually, this brown line actually works quite well. So it's still not matching the joint, but it's working reasonably well. Okay, but when you do more flexible approximation like variational inference, this one is variational inference. So here it's not Laplace, it's like doing more global thing. It performs much worse. Okay? So I'm talking to my community and I'm telling them, oh, if you increase the flexibility of your method, your algorithm should be better, but it does worse. Right? That doesn't make sense. I mean, look at the gap between this, right? It's huge. This yellow line is like really, really bad. So then I say if I write the right algorithm, that actually looks very similar to what I was doing in the simpler case, then this is the red line. So I actually improve performance. You know? So my point is if you bring the principles back to the game, you can actually design methods not by just doing grad student descent, but rather by designing things that will actually really improve things, and you're able to improve that, right? So that's my point. The other thing that we're looking into is that when you know how important the data set is, then you can, when you get the first set of data, then you can identify what is important, and then you don't want to forget that, so you go to the next class, the next task that you get, you regularize it by looking into these points. So you get these lines that don't forget the past. Okay, so this is sort of going into this GP type of thing, but looking into data space and understanding what data points are important, what experiences are memorable experiences. So we call this functional regularization of memorable past, because we are able to define memorable past by just using distributions. It's a slight modification of what people do in deep learning, but then the view is different, that I want to look into the important data points and just remember them. Okay, continue to do that. It works. Okay, why are you going so slow? Sorry, I want to move faster because I'm out of time. If you do this, then it's where is it? Okay, so this was the previous picture that I showed you, and if you add this thing to that, this is like still not using variational inference, but using memorable points. It actually does quite well, so it improves things. And my idea is that now if you add the variational global, hopefully the red and the purple would kind of, either. So the way that you think about the problem, right, and you want to solve it, you don't want to just kind of always start from scratch and using the gradients, and you don't know why things will work better, right? And so we should be doing more of science than empirical stuff, and I hope the principles let you do. So this is the last part of my talk. So we're still very far from how my daughter learns about ukulele and guitar, right? And you remember that when she is exploring things in the beginning, she doesn't know. So Bayesian theory says that you should be exploring with a wide range of things. You don't want to be like very biased right now. So she was doing something like this, touching everywhere. But over time, her posterior distribution concentrates. She knows that, oh, I don't like that. I have already tried it. I like this. And she gets there, right? The way that we run our algorithms right now in deep learning is that we do independent sampling from the world. It's IID. We don't use new samples based on what we know and what we don't know, right? So it's really not like humans or animals, and not really Bayesian. So this is a very simple prototype. There is no paper. This is unpublished, and this will come out. But what this is doing is just using the Bayesian approximation to pick the important data points, and it's just kind of not doing very greedily. So it's slowly doing exploitations. It's slowly figuring it out. And what you will see that there's two classes. So this is square, this is circle, and when you pick a point, it becomes colored. Okay. So if you've seen the point in the past, it becomes colored. And the sample that's selected is by this black thing. Okay. So if I run, you see the classifier right now is 50-50. So it doesn't know much about the world. So it needs to like do exploration. So it touches things here and there, and now it's sort of figuring out. It's like, oh, that looks like one class, this looks like another class, right? And now it's kind of understanding a little bit that if I go this way with this line, some of those points are misclassified. So it's adjusting. And I'm selecting that one point not randomly. I'm selecting the most important one. And now it's kind of not able to make progress. It's like it's pinching. These boundary elements are pinching it. Right? It's saying, oh no, if you move a little bit that side, it gets wrong. So you can't move. Okay? So slowly it's forming opinion, and now it's like the ukulele, string thing. So, okay, so this is just a prototype right now, and there's a lot of work that needs to be done on how should we concentrate things. And the general idea is like Bayesian rules give you this, but then you can't compute the concentration exactly. So we need to look into different views, and we need to be clever and creative in solving this problem. But if you forget the principle, then we'll never get there. So, okay. So hopefully that makes sense. That's the talk. Lots of open challenges, and I'll just kind of say 1 minute on what I think should be done. And this I really say, recommend you to read this paper by Carl Friston, and lots of people in neuroscience don't really like him. I shouldn't say that out loud. It's also recorded. Well, don't agree with him. Anything, and they think this is not, doing the right stuff. But I read the paper, and I have thought about these problems for many years. And when I read it, I could see what I've been thinking about is actually written in the paper. It's really incredible. There are two things in the world. One is how you want to see the world. And this depends on your model. It's about a perception. And the second thing is what you want to see in the world. And it's about acting in the world to change your perception. You're a human being, and you always eat sushi because you're in, Vancouver. But then you want to know how the, other kind of maybe food tastes like. And you could act to go to a different restaurant and change your perception to that. So there are these two things. The problem is that if you knew exactly how you perceive the world, then you can act to appropriately adjust it. But you can't really compute your posterior distribution over it, your belief on how much you know, how much you don't know. So this is a hard problem. So my claim, and Carl Friston also writes about this, is that posterior approximation connects these two worlds. So model is the representation of the world, of how much we know about. So my daughter, when she sits in a room, she only knows about this thing. So this is her world. It's her family, it's her house. And that's all she knows. But maybe she doesn't care about everything in the house. She only cares about the faces of the parents. So she looks at that more. So approximations are like that. You could say attention, but the posterior approximation really tell you like where should I, and they're context dependent. Depending on what I'm doing, they change the concentration. So approximation is actually a representation of what we know. And I think it helps us to kind of see what we know and how we can change that. We don't need to look at everything. We just need to look into this focus place, and we can take this action, and we can change things. So the way that I think about it is that you want to slowly gather data about the world. You want to fill in the data space of what you know and what you don't know. And you can reject certain things by saying, I didn't like that, I didn't like that, I didn't like this, I like this. And then you'll converge. But you cannot be too greedy from the beginning. And this thing is missing in deep learning right now. Okay, so with that, I will end my talk. Tutorial is online. I'll put these slides online as well, so you can check them. A long version should come. This is all with work with Howard Drew, who actually really helped me to form the story on this part. I hope the paper comes soon, but okay. So all of this started with working with Wu, actually. So this paper was in AI Stats, and this has 30 citations. So I hope you will read it and cite it more. But But this really looked like just variational inference, so people didn't pay attention to it. People in my community didn't pay attention to it. But this forms the base. It proposes Bayesian learning rule, in its first form. And this has been sort of then taken to these new papers and taken new forms to reach the audience in a better way. So maybe these papers look a little bit better. There's another paper, if you're really interested in variational inference, this is just a 5-page paper written with Derderick, who is also around somewhere here today. But this paper has a lot of things that community has actually ignored. But anyway, so Aaron actually works here, right? And Ferd now works here. And this is Amari, who works in Japan. Derderick is a visitor whom you might see outside. Wu works here now. And Mark and Reza have worked on this many years ago. 4 years ago, we wrote some papers on this. And Mark and Wu, now we work on many of these things together. And the scaling up to ImageNet paper was done by these guys, and they're all really young people. And the Gaussian process stuff was done with these, and these are like master students, So really amazing work, and lots of lifelong learning stuff comes from Pierre Elkir, who is a member in my group as well. And he's a third edition, so he helps us think about these things. And Howard is a mentor of the group for many, many years. This is the team, and I'm really looking for new interns, and I've always had very good experience, people coming from UBC and doing amazing things with us. So I'll be very happy to collaborate or, do more things together. So if you're interested in an internship, get in touch with me or Mark, send me an email. So that's basically it. Thank you.
Why don't we start setting up? So I guess you approximated 45 minutes by 63 minutes. So we'll take like one question and then we'll go to the final talk. Yes, Samir.
Yes, thank you. So the question is, in a single task problem, would the VOGN or other Bayesian approaches be able to compete with other deterministic gradient descents?
I mean, on ImageNet, I showed the result.
But is there any place where Bayesian approaches fail?
Yeah, model misspecification, which somebody was mentioning. So if the model is not correct, then, algorithmically they fail a lot, right? Because they don't go very well with this deterministic training methods. So they don't work very well. But looking at the theory, I think it just subsumes everything that exists, so it should be fine. At one point it'll work. But yeah, model misspecification is, you have to do certain modifications. So we need exploration on top of this to correct for that. That's my answer. So you need more work. Okay, good. Thank you very much.
All right, thanks, Andy.